Welcome to another deep dive. Today we're going to be looking at open educational resources for physics.
Oh, very cool.
And specifically, we're going to be taking a look at some source material from a 2015 workshop in Singapore, where teachers got to experience these resources firsthand. And we'll be talking about, how these technologies and this new way of thinking about physics education is shaping the future of the subject.
It's really quite remarkable, how these open educational resources have the potential to really, break down barriers
Mm.
and make high quality physics education available to just about anybody with an internet connection.
Yeah, for sure. So let's maybe just start off by explaining exactly what OER are. For people who may not know, can you just break that down for us?
Yeah, so, OER stands for Open Educational Resources, and essentially they're teaching materials that are freely available for anyone to use, adapt, and share. So that can include anything from textbooks, lesson plans, to videos, interactive simulations,
Hmm.
and they're all licensed in a way that encourages collaboration and customization.
So it's like a vast library of free material that's just out there for teachers and students to
Yeah.
use. Yeah, that's pretty amazing, especially for schools with limited budgets
Mhm.
or students who might not have access to traditional textbooks.
Absolutely. And what's even more interesting, I think, is how this workshop in Singapore focused on using a particular type of software called open source physics, or OSP. And this software allows teachers to create and share interactive simulations that bring physics concepts to life.
Simulations, huh?
Yeah.
So can you give me an example? What might one of these simulations look like, and how is it actually being used?
Yeah. So imagine. Um, and there's a discrepancy between an object's actual weight and what's displayed on the scale. So this immediately sparks curiosity. The students start to ask questions like, why is there this difference? Is the scale broken?
Right. So instead of just being told what the number is on the scale, they have to actually think about, what might be going on here.
Right.
Why is there this discrepancy?
Exactly. And it encourages, inquiry-based learning and helps students develop a deeper understanding of concepts like, calibration accuracy, the role of forces like friction, all of that.
Yeah, so it's not just showing the simulation. It's about using that simulation as a springboard
Yeah.
to have these bigger conversations and investigate these ideas.
Precisely. Now, let's move up to the secondary school level here. Things get a bit more complex with a simulation called vector sum. And this simulation helps students to visualize and understand the concept of vector addition, which is so essential in physics.
Yeah, I remember vectors in high school, and I always kind of had trouble wrapping my head around them. They seem so abstract. How does this simulation make it easier for students?
Well, instead of just, looking at equations on a whiteboard, students can actually manipulate vectors on the screen. They can change the magnitudes and directions of these vectors and see how that affects the resulting vector sum. It makes the concept so much more visual and intuitive.
So they can really see that relationship between, the individual vectors and then how they add up to the sum.
Exactly. And to make things even more concrete, the workshop materials actually included a specific example, using some precise angles and magnitudes to show how the simulation can be used to solve like real world problems.
So you're not just, playing around with this simulation. You're showing how it can be used to actually, come up with answers and think about real world situations.
Absolutely. And for even more advanced students, the workshop showcased a simulation called Projectile 2 Cannon, which deals with projectile motion and collision.
Oh, this one sounds interesting. Tell me about this one.
So imagine two cannons that are positioned so they always collide regardless of their starting height.
Okay.
This simulation demonstrates that the collision is predetermined by the laws of physics no matter what those initial conditions are.
So you're telling me like I can change the height of one of the cannons and they're still going to collide.
They're still going to collide.
That's pretty wild.
It really is. It's this powerful visual demonstration of how physics governs the motion of those projectiles, ensuring that they intersect. At a predetermined point, no matter what the initial heights are, the students can play around with different firing angles and velocities. They can observe how those factors affect the trajectory and the point of collision. But those cannons will always collide.
So it kind of challenges your initial assumptions about what might happen, right?
It does, and that's what makes it such a powerful learning tool.
Yeah, that's great.
Now, what's also interesting is that the workshop wasn't just about showcasing these really cool simulations. It also emphasized a particular teaching approach called modeling pedagogy.
Modeling pedagogy. I like the sound of that. So tell me a little bit more about what that is and how it relates to using these simulations.
Yeah, so with modeling pedagogy, you're encouraging students to use the simulations to test their ideas and make predictions about how things work. They're not just passively watching, but they're becoming scientists in their own right, designing experiments within the simulation, observing the outcomes.
So it's about turning that simulation into like a hands-on, almost laboratory type experience.
Precisely. And the feedback from teachers who participated in this workshop was overwhelmingly positive. They were so excited about the potential of these resources, and really eager to share their own adaptations and insights with others.
That's great.
Yeah, and to make things even more, exciting, the Ministry of Education in Singapore was actually directly involved in this project, which really indicates a commitment to incorporating these innovative approaches into the education system.
Yeah, for sure. That top-down support is really important. Make sure that these things actually get implemented and used.
Absolutely.
So we've seen how these simulations can spark curiosity, they can encourage inquiry-based learning, make these complex concepts much more accessible. But I think the bigger question is, what does all of this mean for the future of physics education? How will these resources and approaches actually change the way that physics is taught and learned in the years to come?
That is the question, isn't it?
It is, and it's one that we're going to continue to explore in just a moment. So before we went to a break, we were talking about this exciting shift in physics education, towards more interactive and engaging learning experiences. I'm particularly fascinated by this modeling pedagogy thing that you mentioned. It just sounds like such a powerful way to really help students connect with physics on a deeper level. Can you maybe unpack that a little more for us? Like, what does that actually look like in practice?
Sure. So with modeling pedagogy, you're not just passively watching a simulation, you're actively engaging with it to really build your understanding. So think of it this way. The simulation becomes a virtual lab where you can actually test out your ideas, make predictions, and see what happens.
So instead of just memorizing, formulas, you're actually using them to interact with a simulated world and really see them play out in front of you. That sounds a lot more engaging than just, staring at a textbook.
Exactly. And what I also find interesting is that this workshop, in Singapore wasn't just about the technology. It was also about creating a community of practice. So they actually designed the workshop to encourage teachers to share their ideas, to adapt the simulations, and to really collaborate with each other.
So it was about empowering those teachers to kind of take ownership of the resources and make them their own.
Exactly.
It's fantastic.
And, having the Ministry of Education involved really shows a commitment to integrating these innovative approaches into the education system as a whole.
Right. So we've talked about the why behind these open educational resources and this new approach to teaching, but I think our listeners are probably eager to hear more about the how. So could we maybe dive back into those specific simulations that we were talking about and really explore how they could be used in a real classroom setting?
Yeah, let's revisit that mass scale simulation, the one that's designed for the younger students and shows a discrepancy between the actual weight of an object and what's displayed on the scale.
Right. And that really sparked my curiosity.
Yeah.
I could see how that would instantly get kids asking questions and trying to figure out, what's going on here.
And it's a great way to introduce them to the idea that measurement isn't always perfect. There could be these factors that affect the accuracy of a reading.
So you could talk about things like calibration,
Yeah.
right? And how precise are our tools, or even just, the concept of error in a scientific experiment.
Exactly. And you could even, expand that conversation to talk about the effects of forces like friction, gravity, or even buoyancy if the object were, submerged in water.
Wow. It's amazing how much you can actually unpack with one simple simulation.
It is the beauty of a well-designed simulation.
Yeah.
Now, moving up to the secondary school level, the vector sum simulation provides a fantastic way to make vectors more tangible. Remember, vectors are used to represent quantities that have both magnitude and direction.
Right. I remember those from my physics days, too, and they always gave me a little bit of a headache.
Well, with this simulation, you can actually see the individual vectors, represented as arrows on the screen, and then you can add them together to see the resultant vector. You can change the magnitude and direction of each vector and see how that affects the final sum.
So instead of just, working with numbers on a piece of paper, you're really seeing those vectors interact and combine in front of you.
Precisely. And remember that specific example they provided in the workshop materials. With those precise angles and magnitudes, it shows you how you can actually use this simulation to solve a real-world problem, like,
Wow.
calculating the trajectory of a projectile or the force that's acting on an object.
Right. So again, it's taking those abstract mathematical concepts and making them more concrete and relatable.
Absolutely. And then for those students who are ready to tackle even more challenging concepts, there's that projectile to cannon simulation.
Yeah, that one really captured my imagination. Just the idea that no matter how you adjust the starting heights of those cannons, they're always going to collide. It seems so counterintuitive.
It does, but that's what makes it such a powerful learning tool. It really challenges your assumptions and forces you to think critically about the physics involved.
Yeah, you can experiment with different, firing angles and velocities,
Yeah,
but the outcome is always the same. Those cannons are destined to meet.
exactly, because the laws of physics are actually governing the motion of those projectiles. And this simulation helps you to visualize those laws in action and see how they determine the trajectory and the point of collision.
Yeah, I can just imagine the light bulbs going off in the students' heads as they're working with this, and they start to really grasp the underlying principles.
And those light bulb moments are what it's all about.
Exactly.
But what's even more exciting is to think about how these simulations, combined with the modeling pedagogy we discussed, could really change the entire landscape of physics education.
Right. It's not just about using technology for the sake of using technology. It's about fundamentally shifting the way that physics is taught and learned. Moving away from rote memorization and abstract equations to a much more, engaging experimental inquiry-based approach.
Precisely. And, with the increasing availability of these open educational resources, these powerful tools are no longer limited to just elite institutions or privileged students. They really have the potential to democratize access to high-quality physics education worldwide.
And that's a very inspiring thought. And it sounds like we're on the cusp of a real revolution in physics education. But as with any revolution, there are bound to be challenges along the way.
Absolutely. There are some important questions to consider about things like digital equity teacher training and really the need to balance these new approaches with more traditional methods.
Yeah, those are all crucial points. We can't just, throw technology at the problem and expect everything to magically get better.
Right.
We need to make sure that everyone has equal access and that teachers have the support that they need to really integrate these tools effectively.
Exactly. And those are the kinds of challenges and opportunities that we'll be discussing when we come back after the break.
We've been having a great conversation about how these open educational resources and simulations are really starting to change the game when it comes to physics education. But I think as we wrap up this deep dive, it's important to acknowledge that, with any big step forward, there are going to be some challenges too.
Yeah.
It's not always a perfectly smooth transition when you're trying to revolutionize how we teach and learn.
Yeah, you're absolutely right. I mean, the potential of OER and simulations is really exciting, but there are definitely some hurdles that we need to be thinking about. One of the big ones is that not everyone has that easy access to technology and a good internet connection, to really be able to take advantage of these resources. And we have to be careful because this digital divide could actually make existing educational inequalities even worse.
Yeah, that's a really important point. We can't just assume that everyone has, a laptop and high-speed internet at home. If we want these resources to really level the playing field and give everyone a chance to learn physics, we have to make sure that all students have that equitable access, regardless of, their background or where they live.
Exactly. And even when the technology is there, not all teachers are going to be comfortable using it in their classrooms. Some might need a little extra training and support to really feel good about integrating these simulations and digital tools into their lessons.
Yeah, makes sense. I mean, having access to these amazing resources is one thing, but knowing how to use them well to create those engaging and really meaningful learning experiences for students, that's a whole other skill set. So professional development is going to be key here.
Absolutely. We need to invest in those programs that give educators the confidence to embrace these new technologies and these new ways of teaching. And it's not just about the technical training, it's also about helping teachers really understand how they can use simulations and OER to encourage, inquiry-based learning, those critical thinking skills.
Another potential challenge that comes to mind for me is the issue of quality control.
Hmm.
With so much content being created and shared so freely, how can we be sure that it's accurate and reliable and that it's actually good from a teaching standpoint? how do we separate the good stuff from the not so good stuff?
Oh, that's a great point, and it's one of the tricky things about the open nature of OER. Anyone can create and share content, which can be both a good thing and a bad thing. So we need to figure out some really strong systems for checking and evaluating these resources to make sure they're high quality. And that might involve, things like peer review processes, making sure things align with, those established learning standards, maybe even some kind of certification process for OER that meets certain criteria.
And it's also important to remember that while simulations can be amazing tools, they shouldn't completely replace that hands-on experimentation and the real-world observations. There's still a really important place for traditional labs and field trips in physics education.
Oh, absolutely. Simulations should be seen as, a way to enhance those experiences, not replace them. It's all about finding the right balance and using the strengths of each approach. Simulations can create that safe space to explore concepts and test hypotheses, but there's nothing quite like the thrill of doing a real experiment or seeing a physics phenomenon happening right in front of you.
For sure. So as we look ahead, what are some of the most exciting opportunities that you see on the horizon for physics education?
Well, one area that I think has a ton of potential is personalized learning. With digital tools, we can really tailor those learning experiences to meet the needs of each individual student and their interests so everyone has their own path to understanding. Imagine a physics simulation that actually adapts to how quickly a student is learning and their style of learning and gives them feedback and support in real time as they go.
Wow, that's incredible. It's like having a personal tutor built right into the simulation. That could really help to make sure that every student has the chance to succeed in physics.
Exactly. And another exciting development is the whole world of virtual and augmented reality. These immersive technologies could completely change how we learn and teach physics by allowing students to really experience these concepts in ways that we could only dream of before. Imagine being able to step inside an atom or explore space all from your classroom.
That would be mind-blowing. It's like taking those science fiction ideas and making them real for students. I can only imagine how excited and engaged they would be.
Absolutely, and we can't forget about the power of global collaboration. OER, by their very nature, encourage sharing and creating things together, connecting teachers and students all over the world. Imagine a global network of physics teachers all sharing their best simulations, lesson plans, and ideas, all available for anyone who wants to learn.
It's like breaking down the walls of the traditional classroom and creating this global community of physics enthusiasts, all excited to explore the mysteries of the universe together.
Exactly. So while there are definitely challenges ahead, I think the future of physics education is really bright, thanks to the power of these open educational resources and the dedicated teachers who are embracing them.
It's been a fascinating deep dive into a topic that I think we're both really passionate about. We've explored the why and the how of these OER and simulations. We've talked about the challenges and the incredible opportunities that they present. But as we wrap up today, we want to leave you with a question to think about. How do you think these innovations will continue to shape the way physics is taught and understood in the future?
We encourage you to check out some of the resources we talked about and let us know what you think. The future of physics education is a team effort, and we're all on this journey together.
Keep exploring, keep learning, and keep diving deep. We'll see you next time.